So this is a little bit funny, right? Because equilibrium is generally not harder than non-equilibrium. But this is one of those cases where we did something for non-equilibrium, and we figured out sort of later that it can actually contribute something to equilibrium problems. Well, I mean, it is still much, much cheaper to solve equilibrium problems, but it turns out some equilibrium problems are hard, and the mechanisms that we use to solve non-equilibrium problems are useful there. So this is work that was mostly done by Eitan Eidelstein, who is my collaborator from NRCN, which is a national lab in Israel. He's like, he has some sort of visiting professor position in Tel Aviv, with Emmanuel, who I think is probably taking his child to daycare, and yeah, and the Inchworm was started at Columbia with Andy and Dave. Okay, so I don't need much motivation here, right? Okay, we're all interested sort of in strongly correlated materials. They have a variety of interesting phases, some of which have some sort of orbital nature, and we know that we can learn a lot about at least local correlations about these things from DMFT. So the strongly correlated but locally correlated physics is related to impurity physics. And our fruit fly or favorite model or whatever, maybe the Kupretz or the 2D Hubbard model on a square lattice, whatever you'd like to call it. And we have a lot of good benchmarks for this, a lot of progress that we've seen here, but in general, we'd like to do some other problems. So if you have a material, right, most correlated materials have those electrons in D or F shells. So you typically have about 5 orbitals per shell. If you're lucky and you have some symmetries, they might split into some smaller representations. So you might have a 2-orbital or 3-orbital model. You may not. You may need to treat all 7 orbitals or something like this. And all of these things interact. All of these things are coupled to the effective DMFT baths. And you would like methods to solve this, and this is even before we get into non-local corrections and things like that. Okay, just the local DMFT problem on one side has multiple orbitals. And this turns out to be quite a hard problem. So we are actually going to address that problem in equilibrium. But before that, okay, let's take a brief trek to non-equilibrium. Okay, well, why did we develop Inchworm? Because we wanted to do impurity models that were mostly this Anderson impurity model, okay, just a single or 2 spin orbitals, but they're coupled to multiple baths, or there's a time-dependent potential or something like that. Okay, something that takes you out of equilibrium, and then you want to do real-time dynamics. And when you're doing that, okay, so this is Hamiltonian, you guys are well aware of this. When you're doing that in equilibrium, so about 13 years ago, Philip Werner came up with the hybridization expansion. Again, this grew out of a lot of other things that were done by people in this room. For the Anderson impurity model, he was able to go to amazingly low temperatures, like beta equals 400. There was nothing like this before. It's a Monte-Carlo method, a perturbative Monte-Carlo method. You expand in the hybridization between your impurity and your bath. You could go to extremely high orders very easily, and there was essentially no sign problem. So you could get an imaginary time Green's function that was perfectly clear, and this has had a huge impact on the field. And this works not just for an Anderson impurity model, but for a bunch of impurity models. People now do routinely calculations that have 5 or 7 orbitals or things like that, but it's not quite generic. Okay? You can't solve all problems of this type. It's certainly not extensible to lattice models. Okay, you can't do 100 impurities or something like that, because this method scales exponentially in the number of interacting impurities. But even for a few impurities, it turns out that some problems are hard. Okay, so again, this is what I'm going to talk about. And going again back to real time. In real time, instead of expanding a thermal operator, you expand something like this, and then everything oscillates. Everything changes sign all the time. And this gives you a lot of sign problems that just don't exist in imaginary time. So using the same expansion, the same hybridization expansion from the 2006 paper in real time that has no sign problem at any filling, at any parameters you can think of, you get a horrible sign problem in real time. Okay, so you can go to, so the sign problem is in time. As you go forward in time, at times of order 1, for pretty much anything you calculate, you get complete garbage. Okay, and you can make this garbage smaller. You can decrease the errors at regular Monte-Carlo costs. But essentially, as a function of time, your errors scale exponentially. So this is the dynamical sign problem. And we developed inch-form Monte-Carlo, which Emmanuel talked about a couple of days ago, in order to overcome this. And it works quite well. Okay, so you can see that, at least in a lot of cases, you can really go to long times without the errors exploding exponentially. Okay, now I'll talk. Okay, some of you have heard about inch-form 3 times in the past week, but I'll explain it again. And Emmanuel's guys have actually used this already to do a simple equilibrium DMFT calculation, but in real time, in real frequency. Okay, so you have DMFT in real time, which is nice. It's much, much more expensive than doing it in imaginary time, but you do get real frequency resolution without analytical continuation. Okay, so what I want to do next is talk about how inch-form works. And then we'll get into what happens for multi-orbital models, where these new sign problems are coming from. And I'll explain what we actually have now. By the way, how long do I have until one is made?
Well, you still have 24 minutes before we enter the discussion.
Oh, okay, yeah, good. So yeah, so let's talk about inch-form. So inch-form is actually a general idea. Okay, it's not linked to any particular model or expansion, but I'll explain it with an example because that's easier with the hybridization expansion. This is the first inch-form method that we developed. So the hybridization expansion, I'm sure most of you are aware, but what we do is we look at these objects that are called propagators. Okay, so this is like a matrix element of a trace over the path of E2IHT. And this guy is not a particularly interesting thing in itself, but you can generalize this a bit, right? So if I write E2IHT, an operator E2 minus IHT, then I get an operator at time t. And I can compose Green's functions out of these things. Okay, so out of a generalized propagators, I can construct any sort of observable single time or multi-time that I want. So in order to construct these a perturbative theory for these propagators, we start with a Dyson expansion. And we start with a propagator which is solvable, okay, which is analytically evaluatable. Then we evaluate a set of contributions at different orders that correct. And this gives you a perturbative diagrammatic theory. We can draw our propagator, right? This dimension is time. So the thick line is our propagator, E2IHT, between two sets of times. We have a bare propagator, E2IH0T. This guy is analytically available. And we have a perturbation. Okay, so our perturbation in the hybridization expansion is a hybridization event, and an electron is going from the dot to the leads or vice versa. So we draw this with one end of a hybridization line, and it turns out that these so-called hybridization lines, in order to give you non-zero contributions, they have to end up somewhere back on the time contour. So every hybridization line comes in and out of the contour at some point. And if you could, right, each diagram like this is associated with some number. And if you could sum up all diagrams like this, then you would get the exact interacting propagator. So that's the hybridization expansion. Of course, as you go to longer times, as this thing becomes longer, you get more and more diagrams, and you get a sign problem out of this. And then that depends on whether you're in real time or imaginary time. But what we do in inch form, again, this doesn't depend on which time contour we're using, is we express a long propagator, a long interacting propagator, in terms of a perturbation theory where we already know propagators between time 0 and some initial arrow time. Okay, so the assumption is that somehow someone gave me all propagators between these endpoints in time, and I want to evaluate this longer propagator. So instead of summing up all diagrams one by one, I can write a theory where my first order contribution is just this completely dressed propagator up to my arrow time, and then I have a bare propagator after that. So that already contains all possible hybridization lines between the beginning of time and my arrow. Okay. And then I have to correct that. So for instance, I can draw any possible hybridization line which is to the right of the arrow. I can also draw hybridization lines that cross the arrow. And if I do that, then I have to cut my propagator, the points where these hybridization lines cross. So what happens is that if I have a line like this, which comes into the dressed part of my contour, then this is one propagator, and after it is another propagator. So this line here has all hybridization lines between here and here. Okay, so in order to, so I no longer have lines which come from this part to this part of the diagram, okay, even though they were contained in this longer propagator. So I have to add hybridization lines that cross my hybridization line, which went into the non-interacting part of the contour. Okay. I don't have to add any diagrams that are fully included inside one of these propagators. That would be double counting. Okay, they're already included in there. And I don't have to add any diagrams with some inclusion that's already fully contained inside the interacting part of the propagator. Okay, so a lot of diagrams actually end up getting thrown away. And then you can write a pretty rigorous. Okay, you can make a pretty rigorous statement about which diagrams are contained in the expansion if you want to sum up everything exactly. Okay, so then you have what at least in physics we would call a formally exact expansion. We can write this longer propagator in terms of shorter propagators that are somehow given to us. And if we sum up all diagrams in this inchworm expansion, we get a formally exact expression. Actually, some mathematicians took interest in this and proved it in a not pretty exact, but pretty rigorous, but supposedly fully rigorous way that is really long. But anyway, the proof is pretty simple, and you can read it in our paper. It's just a few sentences, at least the physicist proof. But eventually, what it turns out is like this, okay? You have to sum all diagrams, which are called inchworm proper. An inchworm proper diagram is one that has only sets of hybridization lines, clusters of hybridization lines connected by crossing that have at least one endpoint to the right of this arrow. Okay, that's the diagrammatic rule that you have to obey here. Okay, so let's look at this. Here we have a hybridization line to the right of the arrow. Here, all the hybridization lines are to the right of the arrow. Here we have two clusters, right? They're not connected. The lines don't cross each other, but they each have an endpoint to the right of the arrow. Here we have one cluster. It's connected by crossing. It's crossing in time. And there's an endpoint to the right of the arrow, and so on. Okay, and you can tell that these diagrams are not inchworm proper. So if we sum up all inchworm proper diagrams, we will get the exact propagator at this point. There's no time discretization error or something like that. Again, assuming that you have exactly the propagators up to this point. Okay, so that's what we call the inchworm step. Once you have that, that leads to an algorithm. In the algorithm, we do a series of steps that we call inching. So we evaluate short propagators just with bare Monte-Carlo. If they're short, so this is like solving a short time or high temperature problem, it's very easy. And then we start extending them one by one. And the manual showed in his talk that this is actually done in 2D, right? So there's some more complicated structure of how we evaluate all these things. But this is the general idea. And eventually we get longer and longer propagators. And then the question is really whether we're going to get a sign problem or not.
Sorry, on average, how big is this? How big is this? How many crossings you have at this high order when you inch? So it's usually second order, third order, fourth order. You ever, in principle, it should go to infinite order, but in practice.
In principle, it should, infinite order is the only point where it's exact. In practice, finite order is often good enough.
About what is typically what you do?
Depends on the physics. So the intuition that I can give you, okay, is that, and the manual mentioned this in his talk, although maybe right, it confused Andy a little bit, so we talked about it later. But if you sum up only first order inchworm diagrams,
that's the NCA. So
that's the NCA.
Yes,
you sum up second order, that's OCA.
I know. But I mean, you would definitely do third order, fourth order. But the question is, do you need to go ever to like order 10 or 100?
Yeah. So it depends on the problem. So what you do is you check order by order and you see where you converge. And there are certainly problems where we have to go to order 10. Okay. It's sort of since we have some understanding of the hybridization problem, the hybridization expansion, where it works, you sort of know that at high temperature, deep in an insulator or something like that, sort of NCA will be okay. You go a little further down in temperature, you need OCA, and you go to the metal, you need higher orders. Right? Yeah.
Can I just ask the same question? There are two questions. One, do you limit the order? And
Usually.
second, how does this limit or is maximum order depend on temperature again?
So in real time, it doesn't usually depend on temperature. In
imaginary time, because in standard hybridization, it's linear with beta. Right?
Yeah.
We know.
So this is not standard hybridization, right?
I
Because
understand.
it's resum,
Just asking
right?
how it depends on temperature.
So I don't know how to answer that in general, but what the question is something like when do you go from NCA to OCA to 2CA and so on, right?
Question,
Yeah. And it's that question. It's exactly that question about inform. The only thing that is different here is that here going from NCA to OCA is a factor of 2 or 4 in computation time, right? Whereas usually going from NCA to OCA is a factor of like time squared, right? So if you have 100 points on your time contour, it's like 10,000 times more expensive. So here it's relatively cheap to go up in order, and you can see when you're converged. And that may even give you some intuition about what order self-energy you need in order to get right physics at a particular regime. Did that answer your question?
Typically, this has extremely long tail, so you look like you're almost converged at OCA, but then you add the third order graph, has a little correction, the fourth order graph has a little correction, the fifth order graph has still little correction.
That's right.
So it takes a long time usually to converge.
Yeah, but then the seventh order graph and the sixth order graphs are about the same. You have some error
exactly.
that you're
It's
willing to
still a little
accept,
bit.
and that's eventually it's numerics, right? You have to determine what your error criteria are. But certainly, if you need 30th order self-consistent perturbation theory, this won't work, right?
Excuse me, may I ask you a question?
Yeah.
In some senses, if I will boil down to mathematical analogy, it's Runge-Kut without prediction correction.
Well, so
does it have similar problem to Runge-Kut, which may lead your, if you will increase step by step, may lead you to wrong direction?
So to be Runge-Kutta at the limit where this time is very small, this can be Euler or Runge-Kutta or something like that.
Yes.
Actually, the mathematicians who did this paper, they looked at it from that angle, right? At that limit, they looked at Euler versus Runge-Kutta and things like this. But here, so this has no error in time. Okay? The only error in time that you actually get is the fact that in order to do this in practice, you discretize your propagators and you put them on some grid. But this step is not like Runge-Kutta.
That's what I'm talking about. So you have a grid.
Yeah, but okay. The fact that I can't evaluate operators exactly as a continuous function, this is where my errors come from. They don't come from the propagation. This propagation step in itself does not have an error. Doesn't mean that we don't have a discretization error, but it doesn't come from that like in Runge-Kutta. So this is like an integral version of Runge-Kutta. Okay, you have all diagrams here. And that turns out to be quite important, actually, because we've tried stuff like that. I would call this like Kadanoff bind, right? So at that limit, you would say that this contour is something like G times sigma, right? And then dG to dt is G times sigma. If you try to do that, it's very hard to get this kind of thing to converge. And people have tried this kind of thing for years. We also did it for some kinds of things. So, that little bit of, it's like an O delta t squared error, that turns out to be quite useful.
So I suggest we let Guy continue his talk.
Yeah, okay. Well, that was a bit of question time.
Sure, that counts. That was the discussion time. Obviously.
Okay, so yeah, but I do want to get to the results. Okay, so this is...
Yeah, that would be nice.
Yeah. But, okay, so this is the expansion, okay, and you have this algorithm that comes out of the expansion, and it works really nicely in real time. In real time is a hard problem. Okay, what makes it actually a hard problem? If you compare, right, here I don't label the contour. So this could be a Keldysh contour, a Matsubara contour, or a combination of both of them, like some of the stuff that Emmanuel showed, anything like that. But in practice, if you're in imaginary time, if you're on a tau contour, these hybridization lines, for instance, are going to just be, something times imaginary time Green's functions. So those are convex functions with a single sign, if you're looking at the diagonal part of them. Okay, so for an impurity model that has only diagonal hybridizations, these things don't contribute signs. Okay, they contribute numbers. Okay, you have to sum them up, but they don't flip signs. In real time, these things, so for a wideband bat, they would be something like a sink. So you get like a slowly decaying complex exponent. So every so often, they flip sign, and you get a lot of sign changes, and you get a horrible sign problem because of that. And that just immediately makes real-time propagation a lot harder. So let's look at this in slightly more detail. Okay, this is a very cartoonish representation of what happens in the hybridization expansion. Here's a slightly less cartoonish expansion, okay, because you have states. So in this expansion, you're exactly diagonalizing the dot space, the impurity space. So for an Anderson impurity model, it has two levels, a spin up and a spin down level. So it has 4 states. And you can represent them like this by a dashed line is unoccupied, a solid line is occupied. So you have 4 interacting propagators, 4 non-interacting propagators. You have all these sort of hybridizations that are hybridization lines that start on one spin, okay, rather than the other. And then you can build a set of diagrams that take into account the state space. Okay, so here, this is for an Anderson model. And all of these diagrams turn out to be diagonal in hybridization, okay, because the model basically conserves spin. So if you have an electron of one spin coming in, you have to have an electron of the other spin coming out. Okay? And these hybridization lines stay on one line. And if you do this in imaginary time, these will have no contribution to the sign. Okay? These will be functions with a consistent sign at a given order. If you do it in real time, then they do. If you go to a multi-orbital model, right, then here you would have, right, even for 2 orbitals, you would have more propagators. Okay, you would have more possible hybridization events, because you could have a hybridization coming from one orbital and then going to another orbital. And those things would be like something times an off-diagonal Green's function, okay, the off-diagonal hybridizations. Off-diagonal Green's functions can change sign, even in imaginary time. And that gives you something that is different. Okay, that gives you a new contribution to the sign that doesn't appear in the, say, simpler multi-orbital models. So if you have a model with just density-density interactions and no off-diagonal hybridizations, then it's kind of similar to the Anderson impurity model in this sense. And you should expect to get a good result in imaginary time. If you don't, then something new may appear. Okay, a new sign problem may emerge. Okay, so that was sort of my intuition for thinking that maybe we could actually use inchworm in imaginary time. And now I want to, okay, before that, let's take a brief, okay, since the CDET family is rapidly expanding, I wanted to reserve the letter I. We also have something like this, okay, so you asked me about high orders. It turns out that there's something which is related to Ricardo's CDET idea. And we do this with a slightly different method that we can connect to it. And we can also do fast summation of higher order inchworm proper diagrams. Okay, so in inchworm, your diagrams are no longer determinant. You sum a set of particular diagrams that you need. They're connected in some different sense from what the interaction diagrams are. They're connected by crossing, and you need diagrams that have particular endpoints in particular places. But it turns out you can write an algorithm in order to do that instead of factorial time, right? The naive algorithm is to sum over all possible permutations and filter out the ones that are inchworm proper. You can do it in exponential time. Okay, so again, this is similar to CDET. The CDET algorithm can also do the same thing. So we actually did something like, we did this without knowing about Ricardo's paper, and then we found out as we were doing this. So we started doing comparisons. So we saw that our algorithm is not as good for the interaction expansion, but the CDET algorithm is not as good for this interaction. Although now Olivier is doubting me, so he's going to try something.
Yeah, let's discuss.
But yeah, we can discuss that later. Okay, but well, essentially you get a huge speed up here. So this means that, sort of practically, if before we could sum 10th order perturbation theory, now at the same cost we could sum 20th order perturbation theory or something like that. And This
Why
really
it's
helps.
exponential, not the power law?
Sorry?
Why it's exponential, not the power law?
It's also exponential in CDET. Yeah.
No, why yours is not power law? Because usually for polaron type problems, it's not exponential. Any type of CDET for polarons is
well,
power
this is
law.
not polarons, this is fermions. So this is the
Polaron.
hybridization expansion fermion.
No, I'm talking
Yeah,
about
okay, the structure is similar to a polaron
impurity
expansion, but,
coupled to the Fermi C
yeah.
usually is polynomial, not exponential.
But what is polynomial? I have to sum up all
Polynomial,
permutations.
the calculation of the connected diagrams using determinants is usually polynomial for impurity model.
But for fermion,
For many body fermions, when everybody interacts with everybody, yes, it's exponential. But if there is a polaron type backbone,
Mhm.
or like an impurity backbone, usually because of this backbone,
But maybe
determinants are power law.
a guy has already answered you by saying that the notion of connected for them is
yeah.
different.
Yes, that's why
I'm not sure we're talking about the
Well, I
same
think
thing.
the
because
confusion
for us-
is about the word impurity. I mean, this is your impurity problems and his impurity
I
problems.
perfectly understand what the impurity problem differences are, but there is a backbone, and the diagram is connected through the backbone.
No,
Yeah.
not connected in their sense. That's the point.
No, they have to subtract something, because they have to avoid double counting, but the connectivity is there, always.
Yeah, so the connectivity here refers to crossing. The hybridization lines crossing each other in time. I don't know if you're talking about the same connectivity.
No, I'm just simply surprised it's exponential, not the power law, that's all.
Okay, well, we could talk about it later
Can
if
we
you
leave
know how to
this
do it.
for a technical discussion?
But certainly if you know how to do it in the power law, that would be wonderful.
It's like Dysonia.
So when we first showed this to Ricardo, he actually thought that he could do this in polynomial time, but it turned out not to be correct. If you have a way, then that would be okay. Yeah, so that's my journey into the CDET family. But okay, let's get to the main things because we don't have very long. What I'm going to do now is just break CT-HIB. Okay, break the continuous time hybridization expansion using the absolute minimal model that you can do it with. So this is essentially an Anderson impurity model, except I've connected the two interacting orbitals. So black circles are interacting orbitals, and these are two bath orbitals, and this is a model with just 6 orbitals, so I can exactly diagonalize it. Okay, I can get a very simple benchmark. And this, okay, you can rotate it to another basis, and you get back exactly what you usually think of as the Anderson impurity model. There's nothing special here. And if you calculate the hybridization function here for the parameters that we've chosen, you get something very boring. Okay, you get nothing in the off-diagonal terms, and you get just a constant in the diagonal terms. Now, and this is stolen shamelessly from Olivier's tricks benchmarks, we add a connection here, okay? And now we have a model of the same size, but that has off-diagonal hybridization. So this also modifies the diagonal hybridizations a little bit, but what you see is that the off-diagonal hybridizations will flip sign. Okay? This is really easy to solve in CT-HIB. This gives you a horrible sign problem. Okay, so now let's look what happens. So we're going to take this model and solve it with CT-HIB and with inch-warm CT-HIB in imaginary time at 3 temperatures. We're going to do like an easy one, a pretty hard one, and an impossible one. Okay, and here you have, yeah.
So you took these functions just by choice? Just
This?
choose this function?
Yeah, I just chose parameters that I think they're essentially the same as what you have in your benchmark.
Right.
Maybe
But the delta matrix is still positive.
the delta matrix here is not positive. Here it flips sign.
No, but as a matrix,
As a
Oh,
matrix.
yeah, yeah.
has to be
It's still
semi-definite positive.
Yeah. It's completely semi. I think it's 1, 1, 1, 1. That's
Oh,
the
okay.
delta matrix, yeah. Okay. So what we do here is we look at the diagonal parts of the Green's function and the off-diagonal part of the Green's function. Okay, there's a lot of symmetry here, so there are only 2 different elements. And this is high temperature. And we have CT-HIB, inch-warm CT-HIB, and just exact diagonalization. And you see that everything agrees for the diagonal and the off-diagonal elements. As we go to lower temperatures, you start seeing some, you start seeing maybe some width to the CT-HIB line, but nothing very noticeable. Then you go to, again, you double the inverse temperature, and then CT-HIB breaks down very sharply. Okay, this is qualitative. I'll do a more quantitative analysis in a bit. But what you see is that essentially in inch-warm we continue to get the right result, where CT-HIB breaks down very, it's hard to maintain even ergodicity. So this is a very hard problem that we've constructed, especially in order to break CTF. Okay, but it's a minimal problem. Okay, this is almost an Anderson impurity model. Then we go to a kind of Mori model. Okay, we just did a 2-orbital model, and we repeat the same process. And you see that we get, this is a case where we have a discrete band, so we can do exact diagonalization. You see that we get essentially the right result, but we have some time discretization errors. It's sort of harder for us to converge this. Here there's no benchmark, right? So we just compare against CT-HIB, and CT-HIB breaks down in both of these cases. Again, this is, the parameters are sort of, here they're just chosen in order to maximize the sign problem in CT-HIB. Here, maybe a little bit, right? But not really, right? This is just like almost the same as a standard benchmark. Okay, so we find, at least for 2 preliminary problems, one of which is a real sort of almost realistic impurity problem from multi-orbital physics, that we can go where standard CT-HIB can't. Now, we want to look at this quantitatively. Okay, so this is sort of like, either it breaks down or it doesn't. Where it breaks down and where Inchworm breaks down, this is implementation dependent. Our implementation is a Python script. Okay, it's not at all optimized. It could be 100 times faster just by writing it in a different language. But it's just a proof of concept. But still, what we look at is, in all of these things, we use the same amount of computer time for each one of these things. Okay? It's about the same computer time for ALP CT-HIB and for our Inchworm code. And then, as a function of inverse temperature, we plot the error that we get in Inchworm in green and in CT-HIB. So in CT-HIB, because you have a sign problem here, you get what you expect. There's an exponent. Okay, or maybe this is even slightly worse than an exponent because there's some polynomial factors involved. In Inchworm, what you see, we actually plot the error divided by the inverse temperature. So in Inchworm, you see a flat curve here. That means it's essentially linear in beta. Okay, so our errors increase linearly in inverse temperature. So it's worse than in real time somehow. But that also may be something that has to do with the discretization choice we've made. So in imaginary time, it sort of makes sense to take more points on the edges or something like that. This still may be implementation dependent. But this is essentially the result. And it's in this case, right, the important statement is that we see no sign of an exponent. So when you solve the same problem with Inchworm, the sign problem, the multi-orbital sign problem that we've inserted into here just goes away. So now there's a hope that this can be used in more complicated problems, and we would like to put this in some of the DMFT implementations and see where it leads. So I think, am I out of time, or what did we say?
We are into discussion time.
We are into discussion time.
You are doing quite
Okay.
good.
So yeah, so I'll just put this up.
Yeah.
Okay. But in one sentence, right? We made Inchworm for real time, but what happens in real time is just that things flip sign, and it turns out that happens in some imaginary time problems. And it's just as hard in imaginary time as it is in real time. So this trick, this resummation trick that solves that, seems to also work in imaginary time. And I hope this will lead to interesting things.